My name is Israel Hernandez. I'm a third-year aerospace engineering student at the University of Texas at Austin. I'm going to be the program manager for UAV Austin. So I have approximately 3 years on the team. So I have some knowledge about UAVs. And on the flight line, since being program manager, I will make sure that everyone on the team is doing their tasks accordingly and that we'll be able to accomplish the mission within the given amount of time.
Hi, I'm Rahul Bhatani and I work in the software department at UAV Austin. I'm a sophomore studying computer engineering and I've been part of the team for 2 years now. Outside of the team, I have no experience with UAVs, and this year on the flight line, I'll be doing maintenance of the computer on board and manual image recognition.
My name is Rhythm Sharma. I'm a freshman at the University of Texas at Austin, and on both the development team and the flight line team, I am the mission planner and pilot. I've been with this team for almost about a year now, and before joining this team, I've had no previous experience with unmanned aerial systems.
I'm Bradley Bridges, and I'm the Chief Software Engineer for UAV Austin. I've been on the team for 3 years now, and this has given me a decent amount of experience in UAVs. On the flight line, I will be monitoring our communications and ensuring everything goes well software-wise.
Hi, I'm Amanda. I'm a sophomore in aerospace engineering, and this is my first year involved with UAV. This past year on the hardware team, I've been working to configure, assemble, and track the UAV during flight.
My name is Akshat. I am the hardware lead on the UAV team. I've been with the team for 2 years, and on the flight line, I will be ensuring that the plane is flight ready and advising the mission plan pilot.
Hi, I'm Dylan. I'm the chief engineer at UAV Austin. I've been on the team for 2 years now, and on the flight line, I will be keeping time and ensuring safety.
Hi, my name is Paige Williams, and I'm a third-year computational engineering student at UT. This is my first year in UAV, and I'm an imagery operator.
My name is Bennett Ramirez. I'm a freshman computer science major. This is my first year working for UAV Austin as a junior code janitor. I'm working on the competition for ground station setup.
Hello, my name is Mark Malmer. I will be the safety pilot for the UT UAV team. I have over 20 years of experience flying RC aircraft, around 10 years of experience flying various sorts of UAVs.
For the 2018 competition, UAV Austin has completely re-outfitted its 2017 aircraft to surveillance. Mechanically, surveillance sports a brand new fiberglass nose cone housing a DSL camera and a custom gimbal. In addition, the aircraft has a new payload delivery mechanism. Surveillance runs off of a TICSOC 2.1 with a double redundant power system and onboard telemetry and ground station communication. The image recognition and identification system has also been refined. The expected performance of the UAV team was based on full mission tests and previous year performance. We categorized each task based on our probability of success. We determined that we have a high probability of achieving the mission time, a high probability of autonomous flight and waypoint capture, a medium probability of obstacles. We are attempting the stationary obstacle, but we are not attempting the moving obstacle. As far as object detection, classification, and localization, we have a medium probability of characterization, a medium probability of achieving geolocation, a high probability of actionable, and a medium probability of autonomy, as well as a medium probability of interoperability. We have a high probability of achieving the air delivery and a high probability of achieving full score on operational excellence. The UAV team incorporated several types of developmental tests ranging from autopilot simulations to ground testing and ultimately full mission tests. The team has conducted a total of 5 autonomous flights, 2 of which were full mission tests. The average amount of time spent in manual mode was about 20% of a 20-minute flight. Tuning is done entirely on the mission planner software. Auto-tune was used initially, and then PIDs were manually honed using the fly-by-wire mode while communicating with the safety pilot. About 6 hours were spent tuning the aircraft. A total of 30 waypoints were flown through to test waypoint accuracy, all of which were hit within a 10-meter radius. The average waypoint miss distance was recorded via telemetry logs and found to be 5 meters radially from a target waypoint. The UAV ran an instance of the interrupt server with custom sample data for our field. The mission planner pilot then conducted a full mission test and reacted to the obstacles as if they were from Webster Field. 4 stationary obstacles in total were tested spread over 2 mission tests. All 4 obstacles were successfully avoided. Our obstacle avoidance program is manually triggered and operates only on stationary obstacles. Synthetic benchmarks with 5 stationary obstacles show that the program can plot a new mission in roughly 1/20th of a second on our onboard computer.
So in order to get the clearest image possible from our camera, we needed to find the closest we could zoom in without leaving any large gaps between images taken during flight. Our camera takes pictures at about a rate of 1 image per 1.2 seconds, and at a height of 300 feet, this allowed us to zoom in about 20%. which made a huge difference in our edge detection because when it was zoomed all the way out, it was picking up patterns in the grass around it, and it was leaving a lot of extraneous lines around our shapes. But when we zoomed in 20%, we got crisp lines around our shapes and the alphanumerics inside. So once we identified the significant blobs through edge detection, we sent it through our retrained Inception V3 model, which we trained using about 400,000 computer-generated images. And these images were random colors and shapes and had different alphanumerics on the insides with different blurrinesses and orientations. And we got about a 93% training accuracy using this. So after that, we ran through 135 different images, which had a lot of computer-generated shapes, but also some shapes that you might find on the field that were not targets, such as paintings on a runway or trees or people. And of these 135 images, it correctly identified 117 of them as either not as shapes or their correct shapes. And there were no false positives during this step. So after that, we took imagery that we got from a previous flight. We got 10 shapes back. 7 of them were unique, meaning they weren't just the same target that had been flown over twice. And of these 7 unique shapes, we had 4 that were correctly identified shapes, 3 that were not as shapes that had been falsely identified as a shape, and we ended up missing 2 of our 6 targets.
Due to time constraints, the air delivery system was not tested in a full mission test. Instead, the air delivery mechanism has been tested on the ground. The competition payload is dropped from a 4-story building onto different environments to economically simulate the impact and provide design rationale for the air delivery mechanism. Failure criteria were also tested. For example, the telemetry was cut to test mission failure, and as expected, the aircraft can experience a loss of telemetry for up to 10 seconds. Full mission test. A total of 2 full mission tests were conducted to test the functionality of the SUAS. The local airfield provided ample airspace to simulate a switch area and navigate through waypoints. Images taken with the new camera revealed flaws in the image recognition system due to crisp edges. This data was used to refine the recognition algorithm. Assembly time was determined to be longer than acceptable, so refinements such as external LED indicators and easier battery mounts were made to reduce mission time. Of the 2 mission tests, the team scored 66% and 73% respectively. The average score was 69.5%, but the team believes can reasonably achieve 75% by competition flight given the extra time.